co-chair of Canberra, part of Sydney section of AIAA, and I will be your host and moderator for tonight. And I'd like to welcome all of you to Dr. Raymond Francis's talk. Before we start, just a few things about housekeeping. This talk is organized by AIAA, the Sydney section, the American Institute of Aeronautics and Astronautics, which is a professional society in the field of aerospace engineering. If you would like to know more about AIAA, please check our website, aiaa.org, or if you're in Australia, it's AIA Sydney section. The talk tonight is recorded, will be recorded, and will be available to the AIAA members on our website and possibly on YouTube. So the format of tonight, slightly different from other talks we have. Dr. Raymond will be talking, and if you have questions during his talk, because there'll be a few sections of his talk, please send them to me privately via chat. I will collate the questions and send them to Raymond. You can, of course, ask them at the end of the section, at the end of the presentation during question time if you would like. We will extend the question time tonight because we are expecting quite a few questions. So that's it for the housekeeping. Tonight, welcome to the talk of Dr. Raymond Francis, who is an engineer at NASA's Jet Propulsion Lab in Pasadena. He works in mission operations for the Curiosity Mars rover and is preparing operations for the next, he was preparing operations for the next rover, which was launched this July. He conducts research in autonomy and artificial intelligence for planetary exploration and manages the onboard intelligent targeting software for Curiosity ChemCam laser spectrometer. He has a doctorate in electrical and computer engineering from University of Western Ontario, a master's in physics from Royal Military College of Canada, and a Bachelor of Applied Science in Mechanical Engineering from University of Ottawa. He has experience with European Space Agency and developing experiments for the International Space Station. He's also an airplane and glider pilot and a gliding instructor. So without any further ado, Raymond, off to you.
Okay, very good. And so maybe I can share my screen. Okay, and Tasha, I'll just ask you to confirm that you see that and that you hear me.
Yes, I can see the screen and I can hear clearly.
Okay, then off we go. So, as you heard, we're going to talk about a software system called AEGIS, which is installed on this vehicle here. This is an actual photo of the Curiosity Mars rover. And we'll talk about what it does and how it enhances the science we do on the surface of Mars through a kind of artificial intelligence. So I'll give you the conclusion slide first. This is the bottom line here. What we're going to talk about is AEGIS. It's an intelligent software system that is operating since 2016 on board the Curiosity rover. What it does is that it autonomously selects science targets for the ChemCam laser spectrometer instrument on the rover. And it does that by prioritizing targets according to the preferences of the science team. To do that, it has to interpret complex natural scenes on a regular basis, and it has done a good job of this, understanding natural scenes in images, even as we drive into new kinds of terrain that we haven't seen before. So that's the bottom line. If you're in a rush and you need to go, this is the main thrust of my point for tonight. But if you have time, stick around and I'll tell you the details. So we'll begin those details with an introduction to the mission. So the Mars Science Laboratory mission, operated by the Jet Propulsion Lab for NASA, is the mission that operates the Curiosity Mars rover, the one we saw on the first slide. And as you may remember, this vehicle landed on the surface of Mars in August of 2012, in particular in a place called Gale Crater. which is a few degrees south of the Martian equator. It's a large impact crater over 100 kilometers across. And we had good reason to believe it was an ancient lake. There was evidence from orbit that that might have been the case. And so we landed here. This is the MSL Traverse. If maybe you can see the cursor, which is up here at this place called Bradbury Landing. And then we've driven along this path, a path that has a total length of now about 23 kilometers in those 8 years. And 23 kilometers is, maybe a few days solid hike. The rover has taken 8 years to do it. But we also have done more than drive. We've stopped at all of these named locations and more to make scientific investigations of various detail and duration. And along the way, we've driven across this mostly flat plain and are now driving up the mountain, which here's the view of that mountain from near the landing site. This mountain was selected as a target. It's inside Gale Crater. It appeared from orbit to preserve in its layers of sedimentary rock the history of some 2 billion years of changing environment on the surface of Mars. And we were very interested in the changes of the environment on ancient Mars, and in particular, whether any of those environments were ever habitable. And so that has been the main goal of the mission, is to try and identify a habitable past environment on Mars. And indeed, we were able to do that fairly early in the mission at this place called Yellowknife Bay. We were able to identify features like this. This is a type of rock called a conglomerate. And a conglomerate, especially this type, is a rock that's formed basically by welding together loose material of uneven size. And you can see here large bits, what we call clasts, embedded in this rock. What you're seeing is a gravel bar that formed in a creek at some time in the distant past, then was subsequently buried, and under the weight of overlying material, compressed into a solid rock. It was lithified, as we say. And this, you might loosely say, it's a sort of a fossilized creek bed. This preserved creek bed has since been exhumed and is now eroding out and dropping all of its little gravel pebbles that used to be part of a creek bed, became part of a conglomerate. Now they're a pile of little pebbles here that are eroding under wind out of this rock. Now, these pebbles are rounded, which is to say they must have traveled some distance to get battered into this kind of round shape, but they're also too big and too heavy to have moved that way by wind. So they had to come in flowing liquid. And we have geochemical evidence to suggest that liquid was water. This other image here shows what we call a cross-bedded sandstone. This is the kind of thing that forms in the sand ripples in the bottom of a lake, or it can also form in a similar way under air, sand dunes in a desert. Although we believe this one to be a lacustrine sandstone. This formed under a lake. And so what we have here is the picture of a lake with a creek flowing into it, probably several little creeks here and there, with liquid water that was fairly long-lived. And we also have geochemical evidence that this water was at clement temperatures. It was warm enough to be liquid, but not so hot as to be destructive to living things. And it also had dissolved in it minerals and materials that would have been useful to living things had there been any living things there. So I allude to geochemical evidence for this, and a big part of how we get this geochemical evidence is with a geochemical spectrometer system, and this is ChemCam. So ChemCam is it's become a routine for us, but this was a really novel contribution to a Mars surface mission in 2012. It combines two sensor modes. First is the laser-induced breakdown spectrometer, or LIBS for short. And that is a very technical way of saying that we have a powerful laser that we can point at objects, in this case usually rocks, and put so much laser energy into the surface of a rock, something like a megawatt per square millimeter, that we can actually vaporize the surface of the rock. And when we do that, we create a little bit of plasma, a little ball of expanding plasma. This is an ionized gas that is emitting characteristic wavelengths of light that depend on which atoms it's made of. So we can tell the chemical composition of a rock by vaporizing part of it and looking at the glowing plasma with the spectrometer. And that's what LIBS does. If you look in the lower left here, you can see several little dark spots on the surface of this rock, which have been burned by the ChemCam laser. Now, this image is one that was produced by the second part of ChemCam, the remote microimager, which is sort of the context camera for the LIBS. It's nice to have a geochemical spectrum, but we also want to know where it came from. What did we measure? So it's this spot right here, and this one, and this one. Now, ChemCam looks out at the world through this aperture here, this large circular window on the mast of the rover. That is, in fact, a telescope that we use to focus both the laser and the spectrometer, as well as the RMI, the camera. And in fact, it's got a 15-centimeter diameter mirror, and you can look in this image closely and see that this is indeed a mirror because it is reflecting upside down the horizon of Mars inside the mirror. This image was taken by a different camera on the rover looking back at the mast. Anyway, so we can use this to get the geochemical composition of rock targets that ranges up to 7 meters. And it has become a routine thing for us. We've used it over 800,000 times. These are statistics as of about a couple of weeks ago. Over 800,000 spectra coming from 2,700 individual targets. And this rock would be considered a single target here. Since we landed in 2012. The instrument was developed jointly by the Los Alamos National Lab in New Mexico in the United States and by this Planetary Research Institute in Toulouse in France. And it was the first such instrument that was deployed to Mars or anywhere outside the Earth. So this was quite novel. And I'll say that the state of the art before ChemCam was that you would usually use an X-ray spectrometer, which required you to put your instrument in direct contact with the rock and then hold it there probably for hours while you made a measurement. ChemCam doesn't need to be placed in contact. You can make measurements from several meters away, which means you just have to point and focus correctly. So it's easier for a robotic system to just point and shoot instead of carefully placing something up against the surface of an uneven, rough material. But it's also much quicker. We can make 150 spectra in about 12 minutes, which means in an hour, you can get a solid measurement of 5 different rocks and do a whole geochemical survey of the area around the rover very quickly, which is why it has become such an important part of the way we explore the surface. And ChemCam has provided a lot of that geochemical evidence that I alluded to that tells us what the water in this ancient lake and creek were like. So ChemCam is a very nice tool, but people have to operate this. People have to take these spectra. We have a team back on Earth that does this. And you'll notice these are little tiny points. This image is 1 degree wide. It's a very narrow field of view. And so this spot is much, much narrower than 1 degree. And so you really have to decide where to point this. It's not a wide field imager. It's not a big panoramic camera where you can be rough about which way you point it. You really have to choose where to point something with such a narrow field of view. So this is where we talk about targeting. So normally ChemCam is targeted by specialists here on Earth. There's a team of scientists and technical engineering people who are familiar with the needs of the instrument and its capabilities, but also familiar with what is a good rock to point at. We will not be able to measure all of the rocks in this scene. We have to pick some good ones. And what you're seeing here actually in this scene in the lower left is a panoramic mosaic that's made up of a number of images from the rover's navigation cameras. And those are in fact stereo cameras. So not only do we have this scene, but we also are able to determine the distance to all of these images, so we can focus ChemCam correctly and exclude targets that are beyond the 7-meter range. And all these little green spots are targets that have been identified as potential objects to measure by the science team in this little area here. And this is showing just the beginning of the targeting process here, where some small number of points have been put. In a complicated scene, we might have many more than this, but we also only have time to measure certain ones, so we have to pick good ones. Time on Mars is valuable. And so the team uses the nav cams, but they also have color cameras on the rover that they sometimes use. This is an example image from the color mast camera, and there's a similar camera on the robotic arm called Molly. And so the science team, the operations team, will choose which are good targets for ChemCam and for other instruments. And then they'll model in the software that we have, that is the one where we pick these targets, where to put the laser spots very precisely here. So here's we saw a grid of 3x3 little points on a previous slide, but here we've got a row of 10 little spots all in a line. And as a little note here, we sometimes give these targets names, usually after places on Earth. And so this one, because it's actually going to be measured, has been given such a name. So this is the process. We use images from Mars, which means before we can do ChemCam observations, we have to have previous observations with an imager, usually the NavCam, that have been acquired. That image has been taken on Mars and it has been transmitted to Earth. And then we can use that image to send a command back to ChemCam that says, point at this. This is how we target instruments on Mars. So now we need to step back for some even further context here. How do we schedule such things, and how do we send those commands? So this is a plot of a bunch of little colored boxes that represent the schedule of activities for the Mars rover on Martian day 1719 of the mission. And this was a few years ago, but it's a representative day. A lot of days look a lot like this. So one thing to note is that the Mars rover does its job best during the day, during the solar day on Mars when the sun is up. And we send the commands directly from Earth, which is more or less sunward if you're on Mars, because we're an inner planet from the perspective of Mars. And so when the sun is up, the Earth is up. Not exactly, of course. Earthrise can be a little before or a little after when the sun comes up, but it roughly coincides with the solar day is when the Earth is visible. And if the Earth is visible from Mars, then so are the radio waves that come from Earth and bring commands for the rover. So each day, the rover, once Earthrise has happened, starts its day with uplink of commands from Earth here, kind of in pink. We also have the opportunity to communicate in the other direction. We call that downlink from Mars. And those are represented in green here. These are opportunities to communicate with Earth. And we use these mostly to send the science data back. And the uplink comes direct from Earth, usually, but the downlink usually goes via orbiting relay satellites. And the orbits of those satellites mean that they're only visible to the rover at certain times of day. And so this period here is when one of the satellites is available and another one is available here at this other period. And so these are the main constraints on scheduling your activities on Mars. So we give the commands for today's activities in the uplink, and then the rover goes and does it. And it's going to start with a period of what we call contact science. And contact science means for instruments that are in contact with the rock. Remember I said the state of the art was for an X-ray spectrometer? Well, we still have one of those, and we have other instruments on the robotic arm. And this day we decided to use them, and so they are taking up about an hour here at the start of the day. And then we move on to a period of targeted science. We're going to make different observations with different instruments. This time, ChemCam observations would fit in targeted science, but also other cameras can go in here. And both of these, the arm work and the targeted remote sensing, These are things that require previous downlink of images for targeting. You need to be able to safely place the robotic arm against some object you saw in the nav cams, or safely point ChemCam or other cameras at objects that were seen in previous images. So, all right, we've sent commands. We're gonna do the context science. We're gonna do the targeted science, and then we're gonna be done with this place, and we're gonna drive away to our next location. Then we have our downlink, as it happens. But after the drive, we also have time for post-drive science. There's a lot of time here where the rover is still awake. These are times of day here, so 10 o'clock basically on Mars and 11 and so on. Before the rover goes into its sleep period here, where we go overnight and we save power by not running when you can't take good pictures anyway. We have time here where the rover's awake. There's lots of time, and as I said before, time on Mars is valuable, so we could do science here. But we have driven, and so at the time of this uplink, images of this place where the post-drive location don't exist. They haven't been taken yet. The rover's never been there. And so the surroundings of the rover at this time are not known. And so it's not possible to target an instrument like ChemCam because we don't have any images at the time of the uplink. Now, we can take images, post-drive images here, and send them back, but they won't be available until the next cycle, at the earliest, the next day on Mars. After these images are downlinked, they can be used on Earth, but it won't be until tomorrow's uplink when we could send commands to target ChemCam. So this period here is not available for targeted science. So we have time for science activities. We don't have any information at uplink. We can't do ground targeted science. People on Earth cannot target instruments during this period. How unfortunate. There's another challenge though, and that's just pointing instruments at all at small features on Mars. So this is a Mastcam image showing a scene here where we have a very small object, which is grandiosely called White Cliffs, but it's a little light-toned bit of vein in the rock, and you can see it kind of continuing here along this crack. This is the geochemical evidence I was talking about before. This is a material that was deposited in a crack in the rock. It precipitated out of being dissolved in the lake water, and then it was deposited here. And it is now a solid piece of rock that is distinct from the host rock around it. That's interesting. The geochemists on the mission are very interested to know exactly what the chemistry of this is. And in fact, the chemistry of these precipitates tells us about the conditions of the water that they formed in. But this thing is almost 3 meters away. It's about 1.5 centimeters long, and it's something like 2 millimeters wide. That's a very small object. And you think about something that's 3 meters away and try to point a laser at it and hit it on the first try. And then think about doing that with a robot that's hundreds of millions of kilometers away, and think about all the challenges of accurately pointing a pinpoint laser system. So first of all, we got to point ChemCam with motors and gears on those motors that might have backlash in them. And so there's going to be a little bit of jitter and a little bit of imprecision in that system. But then also, we're not really pointing in the real world. We're pointing in the NavCam stereo world that's built up out of a stereo model that we've created from these 1 megapixel NavCam images. And so there's a limit to how precise that can be. And also, since the rover took those images that we use to represent the world around the rover, since it took those images, the rover may have shifted or settled after it drove to its new position. And of course, the whole rover is a big mechanical, mostly metal system that can undergo thermal expansion if there have been temperature changes. And there are temperature changes daily on Mars. You can have overnight low temperatures on the order of minus 90 Celsius, and then daytime temperatures that might be at or above 0 Celsius. So all of these things conspire to make it very difficult to point a laser system mounted on the top of the mast there very precisely at little tiny things that are far away. And indeed, ChemCam missed this target. You can see that we made 5 points here with ChemCam, a little roster of points. And the target ended up between 0.4 and 5. So that's unfortunate. And you can try again, and we did, and we hit it that time. But the thing is, that's time. Time on Mars is valuable. But even more, if there was a drive scheduled after this targeted science, we wouldn't have been able to measure it again. It would be too late. We would have driven away, and we would just lose this observation. I mean, we'd get some spectra of something else, but not of this little vein in the rock. So we have a couple of challenges here, and this is where AEGIS comes in. So AEGIS is, NASA likes its acronyms, and this one is for Automated Exploration for Gathering Increased Science. So we are going to make an autonomous system that allows us to do science in times that we weren't able to before. And the system was developed some years ago now, and was actually first flown on the Opportunity Mars rover, an older vehicle that launched in 2003 and had been on the surface of Mars for a few years when they were ready to do some technology trials and experiments. And so in 2010, they ran some trials of the AEGIS system on board, and it was pointing the PanCam, which is basically the color science camera similar to MSL's MassCam. But now we're using it for ChemCam on MSL, and we actually use it in two different ways. First, we do autonomous target selection in NavCam images. We look at a scene like this in NavCam that no one has ever viewed on Earth. The image has not even been sent to Earth yet, and we automatically pick the best rocks to point ChemCam at. And on the other hand, we can look at images from ChemCam's own camera, the RMI, the remote microimager, and we can recognize interesting features and repoint ChemCam at it. So in this image here, if the vein is the interesting thing, the vein is not centered in the image, and you'll remember how small those ChemCam points are in an RMI image. If you want to measure this vein, you've got to make sure that ChemCam is exactly centered on some part of this white vein. And we can do that automatically. We can point, take this image, see that it's not centered, and then recenter it automatically. And so these are the two modes that AEGIS runs in on MSL. So this is what it's for. This is the beginning of how it does it. And I'm going to get now into some details of the computer vision algorithms that are inside AEGIS and how it is that we can process natural scenes like this to do autonomous instrument targeting on the rover. So there's a whole targeting logic here about pointing the instruments and how you make measurements with ChemCam and everything, but at the heart of it all, the first thing you need to do is find objects. You need to process images and identify objects and then recognize them as suitable rock targets. And the algorithm that AEGIS uses on MSL as the target finding layer is called Rockster. And Rockster is something we developed in-house at JPL, but you can think of it basically, at its core, it's an edge finder. It goes through the images and finds things that are sharp, clear edges. And if you look in a picture like this is actually from the MER rover, but the camera is almost identical to the one on MSL. You can see that, there's a nice sharp linear edge between these bits of rock and all of this sand surrounding it. And so edges are a good start for finding objects. And what Rockster does is it cleverly, and in a way that is low in computational cost, finds bits of edges and clusters them together into closable loops, little contours we call them, but basically loops of edges. And it makes some guesses about which bits of edge can be joined together to form a closable loop. And if you can find a group of edges that together form a loop, you've probably found a coherent object. So this is what Rockster does to identify such objects. We call them targets. And then once you've found that, you look inside the parts of the image that are contained inside a target, and you can look at the statistics and the properties of those pixels. So the first thing is size. How big is it in pixels, but also the 3D estimate from the stereo. We do this with stereo cameras. And then you can also project that into the 2D frame and say, well, okay, what if you fit a circle or an ellipse in there? how big of an ellipse fits inside this thing is a basic estimate of how large this object is, because rocks are not always of nice round shapes, right? They have very uneven edges here. We can also extract properties like its position from the rover with stereo, or its position in the image, and various coordinate frames relative to the rover. But we can do other things too, like looking at the pixels that are inside that target. Are they very bright? Are they very dark? But also, are they consistently bright, or are they dark and light mixed? So we can look at the average or the standard deviation of the pixel properties, and we can look at their shape. How round are they? How angular are they? Fit an ellipse and find the orientation of that semi-major axis. So is it more vertically or horizontally oriented? These kinds of things. So these are very, very basic computer vision properties that you would pull out of the objects in the image. But as it turns out, you can actually take those low-level computer vision properties and make like linear algebraic combinations of those that approximate the kinds of features that a geologist would look for, close enough to at least be able to, in the end, pick good rocks. And you can also choose which parameters to use daily. So it's not always looking for the same kinds of rocks. The science team can select what we call different scene profiles. Today we're going to look for small dark rocks, or tomorrow we're going to look for larger bright rocks, or rocks that are very round, or rocks that have other properties. We can combine them. We can change them at uplink time. So the onboard process looks something like this. You start with camera image acquisition with the navcam or with the remote micro imager, and you select the pointing of that on the ground, because you have to choose. You have to point the camera somewhere, so that's part of the commanding. When it runs on board, it takes that image and then it analyzes it with Rockster to identify targets. And here Rockster has identified some number of rocks. Then you look at each of those and extract the features that I described and make a table of those. And then you filter targets based on those properties. Maybe you don't want any that are too far away for ChemCam, or maybe you don't want little teeny tiny targets because those are probably just Rockster finding objects that are either too small or kind of spurious edge detections. And then once you've filtered out the bad targets, then you can rank the targets based on the properties that the science team selected. Once you've done that, then we set a coordinate frame. VTT here refers to visual target tracking. It's a separate system that's on the rover that allows the rover to drive towards a recognized object. We've repurposed their coordinate frame because it's a mobile coordinate frame. You can instantiate it anywhere in the rover's environment. So we place a coordinate frame on the target that we've just found using the stereo distance and position information that we got out of the image. And then it's just a matter of pointing ChemCam at the center of that coordinate frame. And we point ChemCam at that VTT target, acquire the science observation, and then we're done. Or not. We can go back, filter again with different properties and parameters, prioritize again on some different scene profile, and take a measurement on a different kind of target. And do that for as long as we have time, or as many different sets of parameters as we want to use today. So this is how it works. And if it was just this, it would be simple, right? It would just be computer vision and artificial intelligence, and you point the instrument everywhere you want, and it's fine. But there are some limitations. There are challenges when you're operating on Mars, even more than I've explained so far. And one of those is that ChemCam is fragile. ChemCam can be damaged by pointing at the sun. It has a powerful telescope to focus the laser. And of course, telescopes are reversible instruments. Light goes out, but light also goes in. And if you point the ChemCam at the sun, you will burn it out and ruin it forever. So you must never do that. And AEGIS, in autonomously, robotically moving the ChemCam around to point first to take the source image, then to take the images that are part of the follow-up and take the spectra. You have to make sure that you never point anywhere, not just directly at the sun, but anywhere even within several degrees of the sun. And in fact, not just where the sun is now, but where the sun might be over the next few days, because if, for example, the motor that moves ChemCam were to jam and get stuck for some reason, and it was pointing where the sun was going to rise tomorrow, then ChemCam would be fine until tomorrow's sunrise, when it would be burned out. And that's not allowed. So you can see a plot here from the same software we use for targeting, showing exclusion zones where you must not point ChemCam. And so you have to be very careful. The algorithm has to know where it cannot point. And that's not just for the target itself, but also for the slew from the target to the next target, or from the home position of the mast to the target. So this is very important. And AEGIS absolutely has to protect ChemCam. So this is a challenge. We also have, so one of the rules on the rover is don't burn out ChemCam. So ChemCam is fragile, but ChemCam is also potentially destructive. It's a powerful laser, and we have a rule that says don't shoot the rover with ChemCam. Remember I said a megawatt per square millimeter. Well, this image on the left is what happens if you shoot ChemCam at a piece of solid titanium. You end up with a little crater in it. And in fact, this is the only exception to the rule of don't shoot the rover. This is the ChemCam calibration target. It's a piece of solid titanium. It has a very clear spectrum. We know exactly what it should be, and we can calibrate the spectrometer. And it's the only place on the rover that you're allowed to shoot. And of course, you might think it's easy to avoid the rover, but Rockster is an edge finder, and the rover is full of sharp edges because it's a big boxy thing that's made of metal, and it looks very different from its surroundings. But also the rover has wheels on an articulated chassis, so they're not always in the exact same position, and it has a robotic arm that can be articulated and moved around, and in fact it could be right in front of ChemCam. In principle, we don't normally put it there, but it can happen. And so AEGIS, on top of all of those other calculations it's doing and all that computer vision work, AEGIS actually has to maintain an onboard model of the rover's current articulation state to know where all the parts of the rover are as viewed from ChemCam, so that it can exclude any targets that are found inside the rover's articulation volume. And what you're seeing here is how we do it on the ground. This is a plot of the nav cams in a they put in a polar projection. And so you see a bunch of rocks here, but you also see this red region, which is the mask overlying the rover. You can kind of see the parts of the rover inside. And these are, you can't shoot in the red zone because that's where the rover is. And all these little green spots are targets that have been selected by the science team. And this is another software tool they use to verify that their targets are not in the collision volume. And you can see that some rocks, even if they're not on the rover, are too close to the rover to be safe. So AEGIS maintains a similar model of the rover's articulation state and does a similar kind of logic to exclude targets that are not safe.
Sorry to interrupt, Raymond. We just have a question.
Sure, go ahead.
Tamara would like to know what kind of laser is used with ChemCam.
Oh, it is a powerful laser. I think it's 1067 nanometers. So yeah, that's what I can say about that, basically.
And the other one.
Yeah, go ahead.
Sorry, go. You finish, and we'll continue.
No, that's all I have to say about that.
Okay. Second question was from Ronak. How does ChemCam work around the problem of target identification if and when the field of view of the nav cam is obstructed by dust?
Oh, yeah. So if we didn't have the nav cams, it would be very difficult to target ChemCam. We do have another set of cameras. So in principle, we could either, if we lost the nav cams because they became covered with dust, which I understand to be the scenario here, then we might have to fall back to either the HazCam stereo. We have these stereo cameras that are mounted low on the front of the rover, and are basically same kind of deal as the nav cams, or potentially the MASCAM stereo. But we fortunately the nav cams are such low resolution that individual grains of dust don't really get in the way. And they also have a fixed focal distance that is about 3 meters out, which means anything that is like sitting right on the lens, a small object like a mote of dust sitting on the lens, is basically so far away from its focal plane that it's not even seen. And so the dust is only going to be a problem for those nav cams if a significant accumulation of dust were to appear on the lens or on the lens cover. And the way we get around that is by storing the mast, which holds the nav cams, in a stow position that has it pointed down so the dust doesn't accumulate on the lens. Give it enough years, and I suppose it will become a problem. And indeed, the mass cams are starting to show some dust accumulation after 8 years. But even still, they're taking beautiful images. And so, fortunately, it's like not really a problem. But as I say, we have some backup options if we lost the navcam stereo. We also have redundant navcams. I should also say that we have a stereo A and stereo B, and we can switch between them. Although we also have to switch the rover's computer to do that.
Thanks. This is the end of the questions for now, so I'll let you continue with the presentation.
Okay. Okay, so we have these challenges. In addition to like processing images of places that no one has ever seen before, and finding rocks in black and white 1 megapixel images and picking the good rocks, and then not breaking the ChemCam and not breaking the rover. In addition to all that, we have a new kind of challenge, which is just getting this thing into the rover. AEGIS was not part of the original flight software of the rover, and so we had to add it on as like an extra software package after the rover was already on Mars. So first of all, it's one thing if you've got a satellite that has one system. It's just got a camera and a radio to talk to the Earth and send the images back. But MSL, the Curiosity rover, is a very complex spacecraft. It's for sure the most complex thing that has ever been sent to Mars. And there are many, many subsystems that interact. And so that's a challenge. The flight software itself is very complicated. We have these safety constraints, the sun safety and the collision, which is what we call the don't shoot the rover problem. But also, like, this is a computer vision system, and we actually don't have much of a computer. There's a very limited onboard memory. The computer has 256 megabytes of DRAM, but only 128 megabytes of sort of active RAM that we can use for processes. And of that, AEGIS is constrained to use only 16 megabytes of them because we don't want AEGIS to take everything over. We need the rest of that RAM to do everything else that the rover has to do in parallel. So 16 megabytes of RAM, and the computer, the rover's main computer, is a radiation-hardened system that runs at 133 megahertz. In fact, the RAD 750 uses basically the PowerPC architecture, which some of you who read computer magazines in the early 90s may remember. So this is a computer with performance specs of a desktop computer from about 1993 or a cell phone from 2002. And so to do what AEGIS does on a computer like that is a real challenge. You cannot waste any memory, and you have to be really choosy about your algorithms. And even then, AEGIS on MSL runs in a few minutes, 2 to 5 minutes typical runtime to find targets. And in fact, probably the biggest cost there is finding stereo, because that is a computationally intensive task. And the way we get around that is we do stereo just good enough. The range to the target doesn't have to be perfect. It just has to be within ChemCam's focal range, like the focal depth of the ChemCam telescope. Also, as it happens, and this is some jargon here, but we use something called the component load, which is a way of adding software into the rover flight software. We were the first ones to do this. And so this was a new process that the mission had not gone through. And there were potential challenges there. In fact, you have to update the list of components in the flight software and blah, blah, blah. The only other, basically this led to a circumstance where if we did this wrong, the rover might not only not be able to do AEGIS, but it might forget how to drive. It would be a fixable problem, but it would have been a hassle. So we had to make sure not to cause that, and and get the mission to accept this idea and work through it with us. Also, this is a very complicated system, all of this itself, but even AEGIS on its own has a lot of parameters, and there's a lot of ways you could potentially use it. And we wanted to make sure that the people who operate ChemCam and who operate the rover would be able to intuitively understand how to use AEGIS in a way that was productive, because if it's too complicated, they won't use it. If it's too difficult, they're not going to use it. And if it interferes with other things or makes the decision process so difficult that it's hard to be sure that it's going to work right, we won't uplink commands. We only uplink commands that we know will work and do what we want. And then the data that comes back from it needs to be understandable to the people who look at the data coming back from the rover. So these are all constraints that we had to deal with. But I will tell you that we did it. And in fact, we deployed the flight software. That software was done and verified and validated in the middle of September 2015. And then we uploaded it just a couple weeks later, sent it by radio up to Mars, and it sat there on the computer like the downloaded install software file. And then we actually installed it on the rover's flight software the next month in October 2015. But then once it's installed, we have to be confident that it actually works. So we had a 7-step process of progressive checkouts where first you just start up the software and you see if it runs. Okay, good. Then you start up the software, take a picture, find targets, but do nothing and just send the results of the find targets. And you say, okay, that seems to work, and it seems to get approximately the right distances, and it's doing the right thing. Stereo works. Okay, good. Then it's find targets, point ChemCam at the targets, take a picture with the NavCam, not with ChemCam. Don't move ChemCam yet. Just point and see if the pointing's right. Then point and take a picture with ChemCam. Then point and take a picture with ChemCam and fire the laser at that thing. And that's sort of the final win. You have to do that on the RMI source version and on the NavCam source version. Once you've done all of that, then you combine the two, and that's how you prove that it works. Once we did that over the course of a few months, we then had to train everybody up on the system and explain how it works on the real rover, and get the final approvals from the mission project leadership. And then it was May 2016 where we turned the keys over to the science team and said, all right, you have a new artificial intelligence system, use it as you see fit. So did they use it? Was it any good to them? How did it work? And so the next part of this talk is judging AEGIS on the following criteria. Is it worthwhile? And it would be worthwhile, and it would be a good result if it did the following 4 things. First of all, does it run safely? And does it run as expected? Does it get us ChemCam observations? Because that was the point. We wanted to get more science. We wanted to use that post-drive science time. But does it get us good ChemCam observations? Does it get us ChemCam measurements on the kinds of targets that we want? And finally, does the science team, the science uplink operations people, do they find that it's useful? Or is this just a fun software novelty that hasn't actually proven to be valuable to them? So I'll give you the bottom line on that. AEGIS has been run 214 times on the NavCam on Mars, and consistently it has successfully analyzed the source image, identified geological targets, chosen the number of targets that we asked it to pick, and then returned ChemCam observations on those targets. And RLR here is a ChemCam code for a combination of RMI libs and then RMI again observations. It is, in all of those times, it has not once has it ever triggered a collision warning, which is to say pointed the laser at ChemCam and had the flight software intervene. It's also never done that on sun safety. It's never pointed ChemCam near the sun. And it has also never given ChemCam a poor estimate of the distance such that the focus seed information that's passed resulted in a badly focused ChemCam observation. So that's good news. That means the data is at least usable, and we're not threatening the safety of the system. So it was first used in May of 2016 on mission Sol 1343, and the results here are as of 2 weeks ago or so, Sol 2923. And so here's the MSL traverse, and all the little red spots are places where AEGIS was used. And of course, it doesn't happen until late in the mission, which is, because we uploaded the software right around here. So we've run it 214 times on the NavCam, and sometimes we do one target with AEGIS, but sometimes we do more than one target, and that's why the total number of targets is higher at 280. And you may remember I said we did over 2,700 targets on the mission. At this point, 1 in 10 targets on this mission were autonomously targeted by AEGIS. The RMI version has been used less frequently, but it has been used. And just another statistic, since we rolled it out, we've driven over 10 kilometers into entirely unexplored terrain, crossing several new geological units, and we're still running with this thing. So I said that the RMI version was less used, and we'll talk about that a little bit. There are 4 times that they use the RMI version, and every one of those times it got a successful measurement, and it put the ChemCam roster right on the vein that they were looking for. This is an example where the initial pointing was here. You can see the image is not centered on this vein, and had they measured here, they would have missed the target. But AEGIS real-time moved it over and centered it on there, and so it worked. And of the 4, I think one of them, they would have hit the target anyway. They got lucky. But the other 3, actually, AEGIS saved that observation. So that's good news. The reason that it doesn't get used all that much is twofold. One, there is a cost associated with this. This happens in the pre-drive targeted time, and that time is really valuable, and it takes a few minutes to, you have to, in addition to the ChemCam observation, you have to spend a few minutes of AEGIS processing images beforehand. So you only do this if it's really important, because you could have spent those minutes getting another observation on something else if you're confident that you can target from the ground. You don't need this pointing insurance that AEGIS provides. So they don't always buy the pointing insurance, but when they do, it works out for them. So this is the RMI version. Now, what about the NavCam version? Or the NavCam version isn't just slightly adjusting targets here that have been chosen by someone on Earth. The NavCam version is picking targets for itself. So how good are those targets? So of these targets here, I'm showing you a pie chart here of what was measured. Was it the thing they asked for? I said that there was a scene profile that would prioritize according to the scientist's desires. And so was the most desired material, which for this scene profile that we've been using since Sol 1400, is outcrop rock that is still welded to the planet it formed on. 77% of the time, all the shots are on outcrop. And another 6% of the time, most of the shots are on there. Sometimes you get one because they've got a small object or something that one of the points or 2 of the points are off on the soil, or there's dirt on top of the rock, and so that gets measured. And the another 9% of the time, it's hitting rock that is loose. We call it float rock, which is also a good measurement, although usually you prefer the outcrop. Now, I'll note one thing about this is that when it's picking float rock, it's usually because there's no outcrop in the scene. Remember, we don't know what's going to be in the NavCam scene, so sometimes there just isn't anything. The other thing is this number 77. 3 years ago, that number was like 95, and the number has gone down because we've driven into terrain where there's very little outcrop. And so Well, you can't expect it to find outcrop when there's none to find. So what is a good number? Is 77 good? Is 95 good? What's a good reference? Well, the comparison we make is what if you didn't have intelligent targeting? What if you just blindly pointed ChemCam at whatever was right here in the same place all the time? In fact, that's what we used to do before we had AEGIS. We used to do a so-called blind targeting where they would just point ChemCam at a specific position off to the right side of the rover and measure whatever was there. So we have gone back and analyzed for every time that AEGIS ran, what if we had done blind targeting instead? How often would we have hit outcrop? For the first couple of years, it was about 95% of the time that AEGIS was getting outcrop. Now, averaged over the last several years, we're looking at more like 77. But if you had done blind targeting, what would you get? And the answer is something like 20%, because there's, you just have to get lucky and have outcrop there. And most of the time, you just hit sand. Now, there are people who are interested in the chemistry of the sand on Mars, but they are not the majority of the mission. And by and large, we're much more interested in these rocks than this sand that blew in from who knows where. So it definitely beats firing blind by like a factor of 4 or so. And so it's getting us better targets than if we didn't have it. Now I'll give you some examples of what AEGIS has done with the NavCam here. And first I'll tell you, I'm going to show you pictures from Mars, and they're going to be all doctored up with annotations about what AEGIS did. The rock that has been colored green was the top ranked thing, and that was measured by ChemCam. The thing that AEGIS ranked highest and that AEGIS pointed ChemCam at and got a measurement. Sometimes there's a second target, in which case that target is colored in orange. All the targets are outlined in blue, and the ones that survived the filtering, remember there's a filtering step after find targets, the ones that survived filtering are colored in red. Now there's a lot of information on these plots, but the thing that really matters is, what did we measure? Which rock did we pick, and where did the laser shots fall? And those are marked with a little yellow spot. So let's take a look at this collection of scenes here. So you can see that we have to deal with some really diverse terrains. Like, it's not, there are computer vision algorithms that are deployed in buildings on Earth, and they detect when a human walks through a door. And they're always looking at the same door. And they just have to detect a human-shaped object in their field of view. But we have a different field of view every time. We have a different scene every time. We have different kinds of rocks and different amounts of rocks and different shapes of rocks. And we have very diverse natural scenes that we have to process. And there's shadowing. And you can see that Rockster's getting a little confused by the shadow here sometimes. This can happen. But nonetheless, Sol 1400, we picked this. In fact, it's basically the only patch of outcrop here that's sticking out from the sand. We picked it. Here, there's lots of outcrop, and it picked 2. And again, it's doing a very good job. Here, it's mostly sand that it manages to find. Only 3 of these things survived the target filtering, and it picked one of them and measured it. And here's some more examples, just showing the diversity of the scene. Little things, big things. Sometimes the rover shadows in the scene, and it has to know not to get distracted by that. And so these are the kinds of things that we have to deal with. But it works. We're getting rocks. We're getting good rocks, and we're getting the kinds of rocks the science team wants. So the question is, are they convinced by that? And one way to measure that is if they use it. And they have, and you saw that they used it 214 times on the NavCam, which is fairly frequently, but like how many opportunities were there to use it? So here are some pie charts this is not for the entire period because this is a very laborious analysis, but we ran this for a period of almost 1,000 sols, something like 3 years. And we looked at every single uplink plan and said, was AEGIS used or not? And if it wasn't, why was it not used? And this is AEGIS in the post-drive NavCam version, so you only use it if there's a drive. So you can see that on single salt plans, almost half the time there isn't a drive. We don't drive every day. So if there's no drive, we're not going to do post-drive AEGIS. And in the multi-salt plans, it's more common to drive, so that's only about 29% of the time. But nonetheless, the biggest reason for not using post-drive AEGIS, there's no drive. But also sometimes there just isn't time in the plan. There isn't enough data volume. We have limits about how much data we can send back through those relay satellites. And so there might not be the data budget to send back additional ChemCam. So there's no point taking that ChemCam data with AEGIS. And sometimes we're power limited. That's less frequent. And in rare circumstances, there was a couple of days when ChemCam was broken and there's no point pointing it around. But for all plans during this 1,000 salt period, AEGIS was used more than half the time, even when there is a drive. And the numbers are even better if you look at just the multi-salt plans when driving is more common. Another way of looking at it is, do we get more ChemCam data? And the answer is yes. For the first several years of the mission before we had AEGIS, ChemCam was averaging about 255 shots per sol, so 255 spectra per sol. And once AEGIS came out, there's a clear inflection in this line, over 300 shots per sol, because we can now do ChemCam measurements in the post-drive period. And so there's just more opportunity to do ChemCam, and they use that opportunity. They do more ChemCam measurements. Now, since we're talking about a computer vision system, we might as well talk about how the statistics about that stuff under the hood. And so AEGIS on the NavCam is, I told you that it's a crummy computer. It takes a little time to run, and that's okay. We budget for that time on the rover, and it gets us a whole lot of ChemCam measurements. But it's basically linear in the number of targets in the scene. So a busier scene will take more time to run. And we have actually an upper limit on the number of targets at 256 because of the size of the memory that we allocate for this. So that's the limit of that axis. But it's basically linear in number of targets, and it's never taken more than about 500 seconds to run. On the RMI, where we don't have stereo, and we usually have fewer targets because it's such a small scene, it's more like 100 seconds to run. But this is more or less as expected, and certainly for the NavCam mode, even 500 seconds is worth spending if it gets you an hour of ChemCam observations. So now enough graphs, let's look at some pictures. This is an example that's very useful from the computer vision perspective of how consistent is this thing. And you see this little animation here. We got an accidental computer vision experiment when we did a post-drive AEGIS when we arrived at this place, and then we planned to drive away from this place with another post-drive AEGIS at the post-drive location, but the drive failed, and so the rover didn't move. And so we got a new AEGIS image of almost exactly the same place. The rover had slightly shifted, but it didn't drive away. So we're seeing the same rocks. And AEGIS actually, not only did it pick the same rock, it picked almost exactly the same spot on that rock. And a nice illustration of why intelligent targeting is better than blind targeting. The default blind target location is here in the sand. AEGIS is smart enough to put the ChemCam on the rock. And it's a good thing for a computer vision system if it looks at the same thing twice and comes to the same answer. You can see that the shadowing is a little bit different. The lighting is a little different between the two scenes, which explains why the target, like the edge finding target layer didn't exactly perform the same way because the lighting is different. But it's in bulk, it's consistent, and that's good news. And in fact, it is very consistent to lighting in general. And so there are two plots here. One is the where is the sun in the sky, which tells you where the shadows are and what time of day and how harsh those shadows are and which direction they're going and how long they are. The other one is angle relative to the rover. And you can see the it's usually, the sun is usually in the west, because we usually, we operate during the day, and the drive is usually near the middle or end of the day, and so the post-drive period is usually in the afternoon, which means the sun is in the west, but not always. And we're at the equator, so the sun is sort of always towards the west, and it's not to the south or the north. But on the other hand, the rover is pointing it in a different direction after every drive, even if we're mostly driving in a kind of southwesterly direction. There's been enough local deviation from that path that the sun could be kind of on every side of the rover, and AEGIS has performed well despite all of these variances in lighting. So that's good for computer vision. A few interesting science results from this. Sometimes we get lucky, and so, for example, ChemCam holds the world record, that world being Mars, for highest concentration of chlorine ever seen in a ChemCam measurement. And it's not because because AEGIS is good at finding chlorine. It's just that this is a rock that AEGIS picked. It's an extra measurement that we wouldn't have made before, but this is proof that we need to take more measurements. Mars is undersampled, and getting extra measurements with ChemCam and AEGIS is valuable, because we would never have known that the rocks can be this chloriney if we hadn't taken this measurement. And so adding additional ChemCam measurements does expand our understanding of the range of variation of the geochemistry of these rocks. And sometimes the measurements that AEGIS gets are so interesting that the team actually follows up with their targeted measurements. So it's picked a rock that's so interesting that the science team, instead of picking targets of their own, actually goes and makes follow-up measurements on something AEGIS picked. And there's been a few examples of this, but in this case, AEGIS saw this. AEGIS saw this in the navcam, pointed ChemCam at this, and took these RMIs. And the chemistry here was so unusual compared to the surrounding materials that the science team followed up the AEGIS target with a named human-targeted observation. And they look like they're in different places, but this is zoomed in 1,000% here. The second measurement is inside the ChemCam roster from the previous target. Another thing that happened that we weren't planning on is sometimes, we talk about AEGIS running during periods when the humans can't. And this was a time when the humans couldn't plan. Excuse me a moment. This was a day when the internet was down, and the team in Los Alamos who was planning the uplink for this and choosing targets couldn't see the targeting images because they weren't able to connect to JPL servers for whatever reason. And so it wasn't possible to select targets and plan out a carefully targeted ChemCam observation. So instead, they just ran AEGIS. They just told AEGIS to pick a target, and then we drove away. So we actually ran the post-drive AEGIS activity pre-drive. And you can do that. You don't have to have driven. And so this allowed us, the only ChemCam measurements that happened at that location on Mars were from AEGIS, and we couldn't have gotten anything otherwise. This is another interesting example where the geology team likes to understand different materials that are around, and it might not be super obvious if you're not attuned to looking at these kinds of images, but there are 3 kinds of rock in close contact in this image. We have a lower unit here that is kind of flaky and eroding in little plates. We have a smooth and slightly darker upper unit here. And then in between, there is a light-toned band of material that is kind of flaking away like this stuff, but is physically and visibly distinct, and it's lighter toned. And these are basically 3 layers of rock, one on top of the other. And to highlight that, here's the boundaries: the upper darker smooth layer, and the lower flakier material down here, and then the light toned band in the middle. So there are three things here, but the time we had for targeted science only afforded us 2 ChemCam measurements. So which 2 do you get? To really understand this environment, you want all 3, but we only have time for 2. Fortunately, AEGIS had already made a measurement of this material up here, post-drive yesterday when it got here. And so we had this in the downlink. We knew that we were getting a target here, so we don't have to spend a target up there. And so instead we measured this one and got the complete geochemical survey. And that hints at some new strategies we can use for exploring when we have post-drive observations like that, because that allows us to do things like shift. Here are 2 plans. You'll remember this graphic from a slide very early in the presentation. We can move observations from the targeted to the untargeted, and from yesterday's targeted to today's targeted block. And this last picture was an example of enhancing today's targeted observations with yesterday's untargeted observations, because they're at the same place with the same instrument. We're just relying on the artificial intelligence to get them. And we can make up for the fact that there's a limited amount of time here. We can follow up on things that we saw yesterday post-drive. We get early information from AEGIS, and sometimes we have the chemistry data down in time, but sometimes this compass doesn't allow us to get all the data, but we at least know where was measured, and so we don't have to pick that rock. And so it allows us to distribute the loads and the tasks between these different periods, and so it gives us more flexible use of the rover's resources.
Sorry, Raymond, I was just wondering if we can speed it up and wrap it in about 5 minutes, because we have actually quite a few questions that
no problem.
people have sent in.
You're right on time, because in fact this is the conclusion slide.
Oh, okay.
So all of that, everything I have to say is that the AEGIS team is very pleased with the performance of the system on board. The science team has also given us very positive feedback. We've got 4 targets where we provided pointing assurance, but 280 so-called bonus observations we could not have done without AEGIS. And these are more than 1/10 of the total ChemCam observations on the mission. And there have been periods where AEGIS is collecting much more than half of the observations during certain phases of the mission since it was deployed. And as I mentioned in recent slides, the AEGIS guided observations are now often informing the observations we do on subsequent sols. So this is very helpful. So this is AEGIS on MSL, and I'll just note that we have another mission coming. Mars 2020 launched in late July of this year, and it's on its way to Mars, a little more than halfway there. And it will include AEGIS from the beginning. The software is already written, and it's ready for the new rover, and it'll steer the SuperCam instrument, which is an enhancement to ChemCam, but it will also be available for other mass-mounted instruments if desired. And you can imagine on further missions after this that anytime humans can't be in the loop for targeting, or anytime it's more efficient to not have Earth in the loop, this kind of autonomy is valuable. Anywhere in the solar system where the light time delays are very long, or where you don't have a lot of communications relay and you don't want to spend it sending targeting images back and forth, or if the mission is very short-lived, you land on Venus and you've only got minutes or hours to survive in that very difficult environment, maybe you want autonomous targeting. So there are a lot of reasons why there are places in the solar system where this kind of thing are useful. I will point out that this was not my work alone. We have to thank the whole AEGIS team, including Tara Estlin, the PI of the AEGIS project, the ChemCam team, the MSL team, and that whole, hundreds of people were involved in this from the MSL, the ChemCam, or the AEGIS side. But here's some key names. And finally, I will leave with one last picture, which is, this is a scene from the December holiday a couple years ago when we shut down for a week and a half. Everybody went home, and AEGIS just kept shooting rocks for several sols. while we were all enjoying our holiday. And this is a thing you can do with artificial intelligence. So that's the end of that presentation. And I'm told that we have questions.
Thank you so much, Raymond. That was quite amazing for all of us.
My pleasure.
Very informative. Lots of questions, as expected.
Sure.
So a couple of members unfortunately had to jump off, but I'll still ask the questions. Have NASA come across any novel elements with the ChemCam from Selosi?
So, okay, so Mars is made of the same stuff as the Earth. It's the same periodic table. There's no new elements there. There are unexpected elements. Both boron and fluorine were seen for the first time on Mars with ChemCam. And both of those speak to interesting chemistry. And manganese is also something that they're very focused on, although I think that was not so much novel as the fact that the place we found it and the concentrations we found it in tells us something about the history of the environment. But yeah, I think those are among the geochemical highlights.
All right. Jory is asking, how do you know that one chlorine measurement was not an error?
Yeah, ChemCam is well calibrated, and that's also not one measurement. That is from a target that would have had about 900 spectra on that rock. And so, some radiation offset in the rover's computer or something might corrupt part of one spectrum, but it wouldn't corrupt all 900. And ChemCam is pretty well calibrated, so we're confident in that measurement.
Thanks. Question from Mark. If the neural networks or trained models are openly available, he would like to be able to work through similar models with his students to identify rock and various features in situ.
Okay, so it's worth noting there is no neural network here. That computer cannot run a neural network like that. And we're not using anything so fancy as a neural network. The Rockster algorithm has been published, and so if you want to use Rockster, you can go find it. It's Burrell, B-U-R-L, et al., Rockster, rock segmentation through edge regrouping is the title of the paper. The AEGIS flight software itself is not open source, because this is the software that controls the Mars rover, and we're very careful about that. However, there is another target finding algorithm that is available, and that seems like the part that you're asking for is finding rocks in images rather than the AEGIS part, which is actually controlling ChemCam and all of that stuff. So if it's finding rocks in images you're interested in, you can go look at the Rockster paper, but you can also go look at the alternate target finding layer, which we have sometimes used with AEGIS, which is called TextureCam, all one word. And Google will find you that with TextureCam and JPL. That has been open source. And you can run that on any computer. You can also run it on a gate array, on an FPGA. And it runs very quickly and does pixel-wise classification. Well, Rockster is an edge finder. TextureCam does pixel-wise classification of images. And that one, it doesn't use a neural network, but it uses a decision forest algorithm. And you can train it to look at all kinds of different things. We've run it on a satellite to classify ocean from cloud from land. We've run it on images of rocks like this. So you can do all kinds of things with that. And I think, and it's open source and available right now. And so it would be a great bet for a didactic tool for teaching students about machine learning and processing of natural environments. And there are even a bunch of papers, some of them me et al., about how to use it in geological environments, and a website with all the code online. So that's TextureCam would be a great place to go, I would say.
Wow, thanks.
Mm-hmm.
So Spanna is asking, what is the ChemCam's laser dwell time to cook up the plasma at the rock sample?
Oh, it's very fast. I think we run at 2 hertz. So 150 spectra in like 75 seconds.
Wow. Spanner, has NASA been approached to release AEGIS for use outside the NASA, like medical imaging?
Oh, that's interesting. I think so. The AEGIS framework itself is very much about instrument pointing and things, and I suppose there might be applications for that. Very commonly in medical applications, the instrumentation is not autonomously targeted. The imaging might be autonomously processed. There are algorithms out there that find tumors in MRI images and XRT images. And you might imagine that something like Rockster or TextureCam would be useful for that. But the next step of saying, we've autonomously processed this image, now let us autonomously point something, let's say therapeutic X-ray or radiation source to like kill a tumor in a human body, autonomously targeted based on finding it in an image. That, I don't know if anyone's doing anything or if anyone's brave enough to do that. I think right now they have humans in the loop to make sure that they are safely using things like that. But the target finding stuff might be useful to people. I think Rockster is very much optimized for like running on a dumb computer looking at rocks. But things like TextureCam are closer to what you might try in medical imaging. Is often a very messy scene. The rocks, we have nice clear pictures of rocks. If you ever look at an ultrasound or an XRT image, they are really, really noisy. And something like TextureCam might do a better job there. Rockster as an edge finder, I think would struggle because you rarely have clear edges in like an ultrasound. So yeah, those are my thoughts on deploying that out there. I am not aware of anyone from the medical community asking us to use either the AEGIS targeting framework for autonomous instrument pointing or the Rockster or TextureCam target finding layers. But TextureCam's open source if they want to try.
Spanner again. How are the optics and all exposed rover moving parts protected against scratching by the nasty sharp-edged Martian regolith blowing in the wind and dust kicked up by the rover wheels? Does AEGIS detect and discriminate junk and scratches on the lenses?
So the kicking up of dust by the rover wheels is not such a problem because we drive so slowly. And also the air is pretty thin, so it's hard to loft dust. You drive down a road on Earth in a thick atmosphere with wheels going tens of kilometers an hour, and you can throw a lot of dust up. But in a very thin atmosphere with wheels going, centimeters a second, you don't really have that problem. There is a lot of dust flying around the atmosphere at times, though. It's a seasonal problem on Mars. And then it's more about that dust when it settles out onto the rover. And I mentioned before that we protect the navcam simply by stowing the mast pointing down. And ChemCam also gets some of that. We have some other tricks. There are places on the rover where there are sensitive instrumentation, and we put magnets next to it because the dust is on average a little bit ferromagnetic, and that can help. And mechanisms and things tend to be enclosed, so that the gears and the motors are well sealed up against the dust. But it is inevitably a problem, and the mast cams, they are exposed, and they have picked up some dust inside the baffles, and so we kind of there are certain times when it's difficult to make very high elevation measurements with the mast cams, for example. But they learn to shake that dust off and do things like that.
Right. Jory's asking continuation of this, the question from before. Were there difficulties with optimizing Rockster for Mars rocks as opposed to Earth rocks?
Yeah, actually, yeah. So rocks are rocks, but rocks look different, right? And the whole point of this is that not all rocks are the same, and that's why we're training this thing to pick different rocks. And yeah, it is very scene dependent. You heard me use the term scene profile, which is to say a collection of parameters for processing a particular type of image. And the profile you use in well, on Earth certainly would be different than what you use on Mars. We tested this in JPL's analog terrain, the Mars yard that we have, where we practice with rovers and with vision systems. But we also we did a lot of the development of the MSL, the scene profile for Gale Crater, using images from the first part of the drive from before AEGIS was deployed, but also images from the MER rover, Spirit and Opportunity, because we had examples of Mars rocks over there. But as it turns out, Gusev Crater and Meridiani Planum look different from Gale Crater, and even worse, the first part of MSL's traverse, the flat floor of the crater, looks different than the rocks on the side of the mountain that we're on. And when we deployed on Mars on Sol, we uploaded around Sol 1100 and then did all those tests for a few months. By the time we rolled it out to the science team, we'd driven into new terrain and we had to update the parameters. And then again, about 2 years ago, we drove into some really new geology and again had to update the parameters. So it's not even a question of Earth versus Mars. It's like these rocks from those rocks over there. When you drive into a new geological unit, you have to update the rockster parameters. And that, AEGIS isn't really a learning system on board. It's an intelligence system, but it's not doing active learning from its environment. We not hard code, but we like specify the parameters at uplink time. But we do have a learning system here on the Earth. We run like supercomputer runs to process all the different rockster and AEGIS parameters to combine to make a scene profile when we have to make a new one.
Right, thanks. Again, question that continues on this note is, you mentioned briefly before that ChemCam was down broken for a few days. Mm-hmm. How is something like this remedied remotely?
Yeah, so, I say broken in a very loose sense. We've had a few different issues. There have been times when the mast that points ChemCam has had faults, and sometimes it's a software fault. And you get into some odd mode, and it's, there are unexpected gremlins that crop up in an 8-year-old vehicle. ChemCam itself is also getting old, and you can every now and then some part of the process in ChemCam skips a beat and the instrument goes into what's called safe mode. It says something unexpected happened. It may have been that some bit of cosmic ray came in and flipped a bit, and now the thing is confused. And so then ChemCam's not available in the next plan until they figured out whether the instrument's still safe. But probably the worst thing that happened with ChemCam was actually a little before we uploaded AEGIS. The focus system failed, like, completely. So ChemCam, as I described, you really, in order to generate that plasma, you have to focus that laser at the correct distance. And the way that they focus ChemCam is that in addition to the powerful laser that zaps the rock, we have just like a laser pointer, basically a very low power laser that is focused through the same telescope, and you image that from the rover with the ChemCam. And if that laser pointer is making a little tiny spot, it's focused. And if it's making a big fuzzy disk, it's not focused. And you can do an autofocus with that. That autofocus laser failed around Sol 800 of the mission. And we couldn't focus ChemCam anymore. I mean, we could focus it, but we couldn't autofocus it. And so you had to guess correctly the distance to the rock. And the challenge with that is that the focal depth of the RMI and of the laser to affect a LIBS measurement is very small, and it's less than the uncertainty in a NavCam stereo estimate. And so if you look at the NavCam stereo and it says, oh, it's 2.2 meters away, that's not precise enough to focus ChemCam. So you can't rely on manual focus. So what they did, they anticipated that this might break someday, and they had a grad student at Los Alamos who had done the math to prepare for this eventuality. And so now the way we focus ChemCam, this is an upgrade that was made after the focus laser broke, is we take an image with the RMI of the target before we focus. We use the NavCam distance to guess how far away the rock is, and you take an RMI image with ChemCam of that target at a focal distance that's a little too close. And you also take one that's a little too far, and in fact, you span that distance with something like 11 images, covering the whole range of depth from a little too close to a little too far. Then you process all those images on board right after they're taken, compute there's a mathematical parameter called the Laplacian score that you can compute that basically corresponds to how sharp the image is. And the sharpest, and you like plot the curve, and then you interpolate, and you find the place of the highest Laplacian score. You fit a sort of bell curve to it, and you can then estimate what the correct distance is to focus ChemCam at that distance. So now we have this image-based autofocus to replace the laser pointer-based autofocus. And so that's an example of how you can fix an instrument from across interplanetary distances. Sometimes it's just a software fix. Sometimes you have to completely change the way you operate the instrument, like we did with the autofocus.
Right, thanks. Last questions. We're running quite late, so and it's late in California. So one last question from Spanner. I'm sorry to everybody that won't get the questions answered tonight. There are quite a few left. As an individual, how do you constrain your curiosity to focus on your NASA job and not just all that's going on around you at NASA? Because there's so many interesting projects.
Oh yeah, no, JPL is an exciting place to work. You know, we have spacecraft all over the solar system. We also have astronomy missions and many Earth missions, and plus there's technology and science research going on here all the time. And so, yeah, there are more projects to do than I have time in the day to do them, which is a fortunate problem to have. You know, it's like AEGIS. You know, there are a lot of rocks. You got to pick the ones that most suit the preferences that were laid out. And I have a certain scene profile for this time in my career, and so I have a way of filtering and ranking projects. But you know, I'm fortunate that JPL actually allows me to work on a diversity of projects at once. So I'm currently working on MSL with ChemCam and AEGIS, but also on Mars 2020. And I'm able to fill different roles there. You know, I manage the intelligent software, but I also just do uplink ops. So sometimes I pick the rocks, and sometimes my software picks the rocks. You know, but I'm also able to take part in research projects. Sometimes I propose and lead them. Sometimes I'm a co-I consultant. You know, they have a project and they want someone who understands operations or intelligent software, and so I'll provide a little expertise there. And so I'm able to actually kind of have this buffet of projects that I'm working on at once. So this is one way of managing that. You know, the fact that there are too many things and not enough time.
Right. Thank you so much for this talk on behalf of AIAA Sydney section. That was genuinely very interesting. Thank you everybody for joining us tonight.